As mentioned in the last episode, the power per pixel is the primary barrier to increasing information camera capacity. We can imagine cameras that capture terapixels per second or even petapixels per second, but such cameras with today's technology might require kilowatts or even megawatts of power, so we need to radically reduce power per pixel if we're going to continue to grow camera pixel count. Conventionally, this has been done with application-specific integrated circuits, ASICs. Umbrella is one of the leading companies making such circuits for cameras. Here's a board made by Rhonda that uses an AMRA system on chip to do real-time encoding of video data streams. So we get H.265 or MPEG encoding. Typically, these systems are going to require 10 to 100 nanojoules per pixel, which works out to something like 1 to 10 watts to run a 1 to 10 megapixel camera. So you're still at an order that is where we would be burning megawatts if we built a petapixel camera. So we need to radically reduce this power per pixel, which is here already done, maybe a factor of 100 or 1,000 better than if it was done in a CPU. But to really radically reduce pixel power, radical solutions and new encoding strategies are needed. Here's an example of an encoder that was done by our group at University of Arizona in collaboration with investigators at Sandia National Labs and the United States Naval Research Lab. So this chip was made at Sandia by Ratkan Sarma. The idea is that we have a blind compressor, so we're not going to look at the image data before we compress it. We're going to feed it into a quasi-random compressor that's implemented here in a photonic integrated circuit, and the compressed data comes out in a single compression layer here, and then any decompression happens off camera. This inverts the traditional architecture of cameras in the sense that traditionally cameras have been processor heavy in the camera head, where the data is compressed into a standard format such as H.265 or MJPEG, and then they're very light on the processing side, on the display side. But in a modern camera, where we're going to capture lots and lots of data, we would rather wait to decide how valuable that data is before we expend the power to process it. So we do this kind of blind compression. This particular chip has the capacity to reduce the encoding power per pixel down to the femtojoule range, which gets into a range where very high pixel count cameras are possible. This is kind of technology of the future. Let's continue in this episode to review the history and structure of current compression before we get into discussing where compression is going next. Computational imaging. Episode 58, Compression, Part 2. So in episode 57, we looked at this pipeline for JPEG compression of still images. We got up to this compression, the quantization step. We've taken the discrete cosine transform of the data and we've quantized it, which has the effect of turning most of the signal components in DCT space into zero. So after we've divided by the quantization table and rounded, we have a few non-zero terms typically centered around the low frequencies, and then we have a whole bunch of zeros. Now we can turn this two-dimensional representation in a block into a linear sequence by following this kind of curve. So we'll go along this curve across the data and turn it into a block sequence, which looks like this. The yellow curve is the block sequence for the original DCT data, and the blue curve is after we've divided by the quantization table and rounded the data. And now you see that we have this long sequence of zeros along the blue curve. And so now we'll turn that long sequence of zeros into a coded data set using run length encoding. So run length encoding was invented in the 1950s. It's described well in this book by Stephen Smith on digital signal processing. The basic idea is where we have a long sequence of similar values, we can tell you the length of the sequence instead of all of the values. And so this is a lossless compression strategy for representing long sequences by compressed data. So the last step of the JPEG compression is, first of all, we go color conversion, DCT, quantization, run length encoding. That's the JPEG algorithm, and it compresses by often by an order of magnitude for still images. Now, of course, in many cases, we're interested in video rather than still images. And so the JPEG or MPEG compression strategy basically uses a JPEG-like strategy with transform coding and quantization on still images, and then combines that with intra-picture and inter-picture estimation using motion. So video compression standards, or the standard video compression standard prior to the most recent neural standards, use this idea of iframes and then motion frames. And so the iframes are encoded individually in something like a JPEG strategy, and then B frames and P frames are frames that use motion from adjacent frames to reduce the data prior to compression, so that the B frames and the P frames use interframe motion to make sparse images, and then those are compressed in a much more efficient way. And so standard compression for video could be by a factor of 1,000 or so. So this is not a course in the mathematics of compression. This is a course in camera design, but we need to be aware of compression as a feature in our systems for understanding how we're going to build digital imaging systems. So that's how compression has worked. How could compression be improved for future cameras? Obviously, the first thing we'd say, well, we'd like better image quality versus bitrate. We'd like to improve the rate distortion curves. But that's not necessarily the most interesting strategy for camera design. Obviously an interesting strategy for image processing. But for camera design, the issue is how can we get more capacity out of the camera? And so this comes up with issues like how do we get image quality versus computational complexity and power? The modern computational camera is itself a computer, like we talked about in the last episode. It's a computer with these sensor resources, and we need to design the computer into the camera. You see that already with what was in the introduction of today's episode, as we make ISP chips that are designed to be built into the camera. But even more significantly, we can think about where we do processing in the computer architecture. It may not be efficient to do lots of processing for compression at the point of detection. It's better to delay the processing until the value of the image is known, or the requirement for reconstruction is known. In modern cameras, many images will never be looked at. We want to record much more data than a human could consume, and so if we're not going to look at the data, let's not spend too much processing power on it. So we might want to do something like the blind compression with very low power, as was shown in the chip in the introduction. We can also think about compression strategies that could have different styles of compression based on the actual image content. So we could compress based on facial structures or vehicles and other ways of knowing the system, or we could do task-specific compression, finding and extracting data that would allow event detection or object detection in the camera itself. Of course, there's a large community studying compression strategies and trying to come up with better strategies. Episode 56, we talked about a challenge, the NITR challenge for image super resolution. Here's an example of a challenge based on improved compression algorithms and learned image compression. This particular challenge uses as a metric the rate distortion curve, what is the image quality as a function of bits per pixel, which is, as we've seen, just one metric of a compression strategy. The underlying idea, of course, is that neural systems offer an improved strategy for finding the latent space of images that could be adapted to the image itself. Here's a slide from back in episode 18 where we talked about the basic structure of neural processing, and in this example we use the neural processing for image demosaicing. So we have a stack of images that come in, and coming out we have the decompressed image. But this process of going from a wide representation of the image at the input to a narrow, just a few features in the UNet representation in the middle, and then decompression is kind of a strategy that we could use for image compression. Here in this latent space, we've represented the image by a small number of features, and we could use those features as our compressed representation and then later use the other half of the UNet to decompress the image. This approach is called an autoencoder, so it's commonly used in the basic structure of image compression. And there's various types of autoencoders, but the basic idea is you go through this bottleneck in a latent space where you represent the data in this compressed format. This has been implemented in all kinds of strategies. Here's an example from Nanjing University of a fairly detailed and deep network that uses optimization of the rate distortion curve to improve compression. And if you look at the rate distortion curves, of course, they look spectacular compared to JPEG. That you get well under 1 bit per pixel in representing the image and good image quality. But as mentioned, for camera design, this metric may not be appropriate because the key limitation on camera capacity is the power per pixel, and the point of compression is to get data off the camera without spending too much power or memory per pixel. So another strategy here shown from our group, where we focused on very, very simple first layers, where we just do blind random compression in a first layer of a neural network to get the encoding, and everything in red here would happen in the camera, and everything in blue here having to do with decompression happens off the camera in the cloud at a later time when you've determined the value of the image. And so what this does is give you image capacity that doesn't exceed conventional JPEG, but can match JPEG. So here we're getting PSNR in the range of 30-ish, matching JPEG for similar compression ratios, but achieving this with much lower power per pixel. So the power per pixel that we measured here in terms of the computer running time is an order of magnitude better with this blind compression, and so this allows us to capture more data. So understanding the architecture of the processing and the computer architecture that's going to manage the data coming off the camera is a fundamental piece of camera design, and ultimately will determine how much data we can record in the camera. We can imagine doing this processing both in optical sampling and in electronic processing, as we've seen here. We'll return to this in Chapter 10 when we talk about sampling strategies in more detail as we go through the basic operations of digital cameras in this chapter. Our next step, though, is to consider how much optical power do we have coming into the camera. I've told you today that we have something on the order of 1 million or 10 million photons per pixel. Let's figure out where that number comes from. And to kind of motivate that thought, I took a picture of this nice little telescope I have sitting around the house. You'll notice the telescope has a sticker on it that says, never look at the sun through this telescope. Let's talk about why that's a bad idea in our next episode.